This program on direct current will cover such material as voltage, which is the pressure that moves the current in a circuit, current, which is the actual electron flow in the circuit, and resistance, which limits and controls the electron flow. As you shall see, for any circuit to function properly, it must have voltage to move the electrons, current to do the work, and resistance to control the current flow within the circuit. We will study the series circuit and learn how to identify them. We will learn how to use Ohm's law to calculate and measure the current, resistance, and voltage drops in a DC circuit. Next, we will study the parallel circuit and see how the characteristics of this circuit differ from those of the series circuit. Then we will study a combination called the series parallel circuit. We will use the information we gain from the two separate circuits to calculate for the current, resistance, and voltage measurements in the series parallel circuit. We will also review the digital multimeter and learn how to properly use it for making the various tests and measurements required for troubleshooting electrical circuits. In this program, you will also learn how to read the color bands on a resistor. Resistors are used in almost every electronic circuit. The resistor will perform many functions, two of which are as current limiting devices and as voltage dividers in a circuit. All matter has electrical properties. This is why engineers over the past several decades have been able to develop thousands of devices that generate, store, control, and switch electricity. The diode, transistor, and integrated circuits are but just a few of these devices. The best way to understand electricity as an essential ingredient of matter is to understand the nature of every element, the atom. The atom consists of a nucleus made up of protons and neutrons. The atom also has electrons that encircle the nucleus. The electron has a negative electrical charge, and the proton has a positive electrical charge, while the neutron has mass but no electrical charge. Normally, an atom has an equal number of electrons and protons. As long as this balance exists, there is no electrical charge. It is possible to dislodge one or more electrons from most atoms. This causes the atom to have a positive electrical charge. It is then called a positive ion. On the other hand, if a stray or free electron combines with a neutral atom, the atom will have a negative electrical charge. It is then called a negative ion. Electrons can either rest on a surface as they do on the plates of a capacitor, or move through a material as they do in a resistor. Each has its place in the field of electronics. When electrons form on a surface as they do on the plates of a capacitor, it causes the surface to become negatively charged. Since the electrons are not moving, the surface can be said to have a negative static electrical charge. On the other hand, the current will continue to flow through a resistor as long as there is a voltage being applied forcing the electrons through the device. This is referred to as dynamic current flow. Most of the time, static electricity is not desired in electronic circuits because it can and will cause severe damage to electronic devices. Therefore, special care is required when handling printed circuit boards which contain solid-state devices. Materials used in electronic circuits are usually classified as conductors or insulators. There is also a third type of material used, which is referred to as semiconductor material. We will discuss semiconductor materials in another program. What is a conductor? Any material which electrons pass through freely is called a conductor. Conductors include such materials as gold, silver, copper, iron, aluminum, and most metals. Conductors are used to connect the various components together to form a useful circuit. On the other hand, an insulator is a material which electrons pass through poorly or not at all. Insulators include such materials as glass, plastic, wood, rubber, mica, porcelain, leather, and paper. Insulators are used to insulate voltages from ground potentials and other devices. Insulators are used on electrical devices for our protection, as well as to protect the device from shorting to ground and damaging the circuit. When an electric current flows through a wire, it creates a magnetic field around the wire. This field is referred to as an electromagnetic field. Also, when a wire passes through a magnetic field, it induces a voltage into the wire. This is a very desirable effect of electricity. If it were not for this effect, electronics as we know it would not exist. It is this magnetic field that makes motors, transformers, coils, analog meters, and many other devices work in electronic circuits. For any electrical circuit to operate properly, it must first meet certain requirements. First, there must be a power source from which the electrons may leave and return. The power source could be a battery, a solar cell, a power supply, or any device which generates an electrical voltage. The power source produces the pressure which forces the current through the circuit. The power source also produces the current which flows through the circuit. Next, we must have a load which uses the electricity that is produced by the power source. The load could be a light bulb, resistor, motor, transformer, integrated circuit, or any other device which uses electricity. We must also have a way to connect the power source to the load. Therefore, we need some form of conductor. Remember, a conductor is anything which allows the electrons to flow through it easily. Wire is a commonly used conductor. Another common conductor is the copper-clad foil used on printed circuit boards. The conductor allows the electrons to leave the power source and travel to the load, then back to the power source. This creates a closed-loop path for the electrons to flow and perform the job the circuit was designed to do. The power source, load, and conductors are all that is required to make a simple electrical circuit function. Now that we've seen what it takes to make a functioning circuit, let's find out what voltage, current, and resistance are and see how they relate to one another. A mathematical relationship between voltage, current, and resistance was found to exist by George Simon Ohm in 1846. This relationship was a most important discovery in electricity, and it was named Ohm's Law in his honor. The equation for Ohm's law is voltage over current times resistance, or simply stated, E over I times R. E represents the voltage, I represents the current, and R represents the resistance. We shall see that by knowing any two of these three variables, the third can be calculated very easily. Before going any further into Ohm's law, let's learn a little bit about voltage, current, and resistance to find out how each of these affect the circuit. The first variable we shall look at is the voltage, which is represented by the letter E in the Ohm's law equation. Other technical terms for voltage are electromotive force, difference of potential IR drop, and volts. Of these, the term volt and voltage are the most frequently used. Voltage is measured in a unit called the volt and can be thought of as the pressure which causes the electrons to flow in the circuit. Without this pressure, the electrons would not flow. The greater the pressure, the more the electrons will flow through the circuit. If the resistance does not change and the voltage doubles, the electrons flowing through the circuit will also double. The next variable we shall look at is the resistance, which is represented by the letter R in the Ohm's law equation. Resistance is the opposition to the electron flow in the circuit and is measured in a unit called the ohm. When the resistance of a circuit drops to zero, it is called a short circuit, and it causes the power to produce a high amount of current. If the power source can produce enough current, it will burn the conductor open, which in turn will cause an open circuit and will no longer allow the electrons to flow through the circuit. A short circuit can also destroy the power source. There are various types of resistors. Some of the more common types are carbon, wire wound, and photoresistors. Carbon resistors make up the majority of the resistors used in modern circuits. Wire wound resistors are used as precision resistors and in high power applications. Photoresistors, on the other hand, are light sensitive devices. The resistance of the photoresistor will decrease as the intensity of the light source is increased. This gives the photoresistor capabilities far beyond that of a regular resistor. Resistors come in fixed and variable sizes. Here we see two types of variable resistors. One is called a rheostat and the other is called a potentiometer, or simply pot for short. If you notice, the rheostat is a 2-wire device and the potentiometer is a 3-wire device. The rheostat has one fixed terminal and one variable terminal. The potentiometer, on the other hand, has 2 fixed terminals and 1 variable terminal. Variable resistors are used for adjusting circuits to meet certain requirements. Here we see the schematic symbol for the fixed resistor, rheostat and potentiometer. The rheostat and potentiometer each have an arrow pointing toward the resistor body. This is the variable lead of the device. The third variable we shall look at is the current, which is represented by the letter I in the Ohm's law equation. Current is measured in a unit called the ampere, or amp for short. Current is the actual electron flow through the circuit. It is the current which flows through the device which makes the device useful. As you recall, Ohm's law gave us the equation of E over I times R. We have now learned that E represents volts, I represents the current, and R represents the resistance. We also found out that current is the actual electron flow through the device. Therefore, if we have a given voltage being applied to a fixed resistance, we can calculate for the current flowing through the device by knowing the voltage and the resistance. For example, if we have a voltage of 1 volt being applied to a resistance of 1 ohm, we will have 1 amp of current flowing through the device. This was calculated by using the Ohm's law equation I equals E over R. This translates to 1 volt divided by 1 ohm, which equals 1 amp of current. When working with electronic circuits, the current flow is usually very small, so there is a kind of shorthand used to represent these smaller values of current. We have the milliamp and the microamp. Usually the term milliamp is printed with a small letter M followed by the letter A. 1 milliamp is equal to 1/1000th of an amp of current. The microamp is usually represented by the Greek letter mu. 1 microamp is equal to 1/100000th of an amp of current. You will see these two terms used a lot in schematic diagrams. Let's pause for a review of the material covered so far. So far, we have seen that voltage is the pressure that moves the electrons through the circuit. We have also seen that we must have resistance to limit the amount of current flowing through the circuit. Also important to remember is that current is another term for the electron flow through the circuit. By using Ohm's law, if we know the value of the voltage being applied to the circuit and we know the resistance of the circuit, we can calculate for the current by dividing the resistance into the voltage. Also, if the current and resistance of the circuit are known, we can calculate for the voltage by multiplying the current times the resistance. And finally, if we know the voltage and current, we can calculate for the resistance by dividing the current into the voltage. As you now see, by knowing the value of any two of the variables, the third can be calculated very easily. Incidentally, an easy way to remember Ohm's law is to write down the equation and then simply cover the unknown value and do what the instructions say for the other two values. For example, cover the E with your hand. You instantly will see the I times R, or current times resistance, to determine the voltage. Cover the I, and the formula becomes E over R, or resistance divided into voltage. And finally, when you cover the R, the formula is simply E over I, or current divided into voltage. Now to continue the program, let's get away from Ohm's law for just a moment and look at the voltmeter. This meter we are using is referred to as a DMM. That's short for digital multimeter. The DMM is a highly accurate piece of test equipment and is capable of measuring AC volts, AC amps, DC amps, and resistance in ohms. No test bench should be without one. There are certain precautions, however, which should be observed each time you use a digital multimeter. First, make certain the meter is set on the proper unit of measurement: AC volt, DC amp, DC amp, or resistance. Second, make sure the meter is connected properly in the circuit for the test being performed. To measure the voltage drop across a component, the meter should be placed in parallel with the device under test. To make current measurements, the meter must be placed in series with the component so the current flows through the meter and the component under test. When measuring resistance, make sure no voltage is being applied to the device being tested. If the value to be measured is unknown, then set the digital multimeter so it is on the highest scale for the unit being measured. Then work your way down to the most accurate reading. After you have completed the test or measurements, it is a good idea to set the digital multimeter to its highest AC volt setting. Resistors use color bands to indicate the value of the resistor. The first band represents the first digit of the value of the resistor. The second band represents the second digit of the resistor's value. The third band represents the multiplier, or number of zeros following the first two digits. The fourth band is used to represent the tolerance of the resistor. The tolerance is the accuracy of the resistor. By using the resistor color code, you can read the value of any coded resistor on a printed circuit board. If there is a fourth color band, it will be gold or silver. As you notice, the colors from 0 to 9 are black, brown, red, orange, yellow, green, blue, violet, gray, and white. I'll give you a moment to review this color code. Resistor values are often measured in thousands and even millions of ohms. For this reason, a kind of shorthand is used to simplify these large values of resistance. The capital letter K, which is short for kiloohm, is used to represent thousands of ohms. The capital letter M, which is short for megohm, and is used to represent millions of ohms. Also, the Greek letter omega, which looks somewhat like a horseshoe, is used to represent ohms. Here we see four resistors. The first resistor has a color code of brown, black, brown. Since the color brown represents a 1, then the first digit is a 1. Black represents the 0, so the second digit is a 0. And since brown is again used for the third band and represents 1, that means 1 trailing 0. Therefore, this resistor with a color code brown, black, brown has a value of 100 ohms. The second resistor is color-coded brown, black, yellow. The first digit is a 1, the second digit a 0, and there will be 4 zeros following the first two digits. The value of this resistor would be 100,000 ohms, or 100 kiloohms for short. The third resistor is color-coded brown, yellow, brown. The first digit is a 1. The second digit is a 4, and there will be 1 trailing 0. That means this resistor has a value of 140 ohms. The last resistor has a color code of white, black, blue. The first digit is 9, the second digit is a 0, and there will be 6 trailing zeros. That means this resistor will have a value of 90 million ohms, or 90 megohms for short. Since all these resistors have a fourth color band of silver, they will all be accurate to within 10% of their rated values. Now remember, the capital K is for kiloohms, the capital M is for megohms. Now to begin our study of the series circuit. When the electrons flow through the negative side of the battery and go through every component in the circuit, then flow back to the positive side of the battery, it is called a series circuit. To figure total resistance for resistors in series, you simply add their values together. This series circuit contains 3 resistors. R1 has a value of 100 ohms, R2 has a value of 140 ohms, and R3 has a value of 100 ohms. Therefore, the total resistance of this circuit would be 340 ohms. This will be calculated by adding R1 plus R2 plus R3. We will assume that these are all 10% resistors. Therefore, the actual value of the total resistance could be anywhere from 306 to 374 ohms. These values were calculated by subtracting 10% from 340 ohms and by adding 10% to 340 ohms. Remember, the fourth band indicates the accuracy of the resistor. Now that we have calculated the total resistive value for this circuit, we will use a digital multimeter to verify our calculations. First, make sure the meter is set on the proper unit of measurement. Then make sure there is no voltage being applied to the circuit under test. As you notice, our DMM shows that we have a total resistance of 340 ohms in this circuit. By measuring each resistor individually, the total value of the three resistors should equal the value measured across the three resistors in series. When we measure R1, we see that R1 measures 100 ohms. When we measure the resistance of R2, our DMM shows that R2 has a value of 140 ohms. Finally, when we measure the resistive value of R3, it shows that it is 100 ohms. When we add these three values together, 100 ohms from R1, 140 ohms from R2, and 100 ohms from R3, we acquire the sum of 340 ohms, the same value when we measured all three resistors together. Now that we know the total resistance of the circuit, we will measure the voltage across the circuit and calculate for the current flow through the series resistors. Before we take the voltage reading, we must set the DMM to read DC volts. To accomplish this, we will place the meter on the DC volt scale and set it on the 20 volt range. When we connect our meter to the power source, it shows that we have 1.5 volts DC available. Now we know the resistance of the circuit is 340 ohms and the voltage being applied to the circuit is 1.5 volts. By knowing these two values, we can calculate for the current flow through the circuit. We accomplish this by using Ohm's law, formula I equals E over R. When we divide 340 ohms into 1.5 volts, we acquire a value of 0.004 amps, or 4 milliamps, which is used to indicate 4/1000th of an ampere of current. Now that we have calculated the current flow, we will verify our calculations with the digital multimeter by measuring the current flow in the circuit. When the voltage of a component was measured, we placed the meter in parallel with the component. In other words, the current flowed through the meter as well as the device under test. The current actually had two paths to flow in at the point of test. As you can see, when the meter is used to measure current, it must be placed in series with the circuit under test. This way, the current flowing through the circuit must also flow through the meter. As you noticed, the meter shows 4 milliamps of current flowing through the circuit. Even if we change the location of the test measurement, it would still show 4 milliamps of current. This is because the same current flows through every component in a series circuit. Now that we know the current flow through the circuit and we know the values of each resistor in the circuit, we can calculate for the voltage drop across each resistor in the series circuit. Once again, we will use Ohm's law to calculate the voltage drop, current times resistance. When we multiply the actual current flow of 0.00441 amps times the value of R1, which is 100 ohms, we get a voltage of 0.441 volts. Therefore, R1 will have a voltage drop of 0.441 volts. When we multiply the actual current flow of 0.00441 amps times the value of R2, or 140 ohms, we show a voltage drop of 0.618 volts across R2. And when we multiply the actual current flow of 0.00441 amps times the value of R3, 100 ohms, we get a voltage drop of 0.441 volts across R3. By adding the voltage drops of R1, R2, and R3, we get the sum of 1.5 volts, which is the voltage of the power source. Now that we have calculated the voltage drops across the three resistors, we will use the digital multimeter to verify the calculations. The digital multimeter shows the voltage drop across R1 to be 0.441 volts. The voltage drop across R2 is 0.618 volts. And the voltage drop across R3 is 0.441 volts. When we add these three values together, we acquire the sum of 1.5 volts, which is the voltage of our power source. We have reached the midpoint in our study of direct current. We will now do a short review of the material covering the DMM, resistors, and series circuits. You have seen that the digital multimeter is a very useful piece of test equipment. However, there are certain precautions which you should be aware of when using the DMM. First, the meter should always be set for the proper unit of measurement and should be connected properly to the circuit for the test being performed. When making resistance measurements, make sure that all power has been removed from the device under test. In a resistor, the first two color bands indicate the first two digits of the resistor's value. The third band is the multiplier. The fourth band indicates the tolerance. You have seen when the same current leaves the negative side of a power source, travels through every component, and returns to the positive side, we have a series circuit. Now that we have examined the series circuit, let's see what a parallel circuit is and what makes it different from the series circuit. In a parallel circuit, there are several paths or parallel branches through which current may flow. As the electrons leave the negative side of the battery and proceed through the circuit, some of the electrons will flow through R1, some will flow through R2, and some of the electrons will flow through R3. After the current flows through all the parallel branches, it recombines and returns to the positive side of the battery. As you can see, parallel circuits are easily identified because the current may flow through one branch or flow through another branch. If you remember that in a series circuit, the same current flowed through every component in the circuit. Since the current which leaves the power source must divide and flow through different paths, the current in any branch of the parallel circuit must be less than the total current supplied by the power source. Here we see a parallel circuit with 4 amp meters. The first meter is used to measure the entire current flow through the circuit. The 3 remaining meters read the current flow through each individual branch. If you noticed, each component in our parallel circuit is connected directly across the power source. Since the current flowing through one parallel branch does not pass through the other parallel branches, the current taken by one of the branches will be completely independent of the other branches. As long as the applied voltage does not change, the current flowing through a parallel branch will not change. Even if a branch is removed, the current flowing through each of the other branches will remain the same. The only value that will change will be the total current drawn by the circuit, as was indicated by the amp meter in series with the battery. Kirchhoff's current law states that the total current entering a parallel branch must equal the current leaving the parallel branch. In other words, if 4 milliamps of current enters a parallel branch and divides and flows through the different paths and then recombines, then the 4 milliamps of current must also leave the parallel branch. The voltage drop will be the same for all components in a parallel branch. If you recall, in the series circuit, the voltage drops changed, but the current always remained the same. Whereas in a parallel circuit, the voltages will remain the same, but the currents will change. This is because the current has more branches to flow through, and the resistance of each branch will determine the current flow through that branch. To determine the total resistance of a series circuit, we simply added the resistance values together, but in a parallel circuit, we must calculate the total resistance differently. There are 2 common formulas used to calculate for the total resistance of a parallel branch. The top formula is used to calculate circuits with 3 or more branches. The bottom formula is used when there are only 2 branches in the parallel circuit. By using either of the 2 formulas, along with Ohm's law, and by knowing Kirchhoff's current law, you can calculate the circuit characteristics of any parallel circuit. By using Ohm's law, we can calculate for the current flow through each branch of a parallel circuit. We will use the formula I equals E over R. As you recall, the voltage drop across each branch in a parallel circuit will be the same. Therefore, we know the resistance and the voltage of a branch, so our formula becomes I equals 1.5 volts divided by 100 ohms. When we divide the resistance into the voltage, the net result is a value of 0.015 amps or 15 milliamps. This is the value of current through R1. Once again, using Ohm's law, we will figure the current flow through the second branch of the parallel circuit. Our formula now becomes 1.5 volts divided by 140 ohms. This gives a value of approximately 11 milliamps. This branch actually has 10.7142 milliamps of current flowing through it. We will now calculate for the current flow through the third branch of our circuit. Once again, we divide the resistance into the voltage. The net result shows that there is 15 milliamps flowing through the third branch of the circuit. Now we know the value of current flowing through each of the branches in the parallel circuit. We can use Kirchhoff's current law to calculate for the total current flow of the circuit. When we add the 3 branches together, we get a total current flow of approximately 41 milliamps. Since we know the applied voltage and the total current flow through the circuit, we can calculate for the total resistance of the circuit. To do this, we will use Ohm's law formula R equals E over I, or resistance equals voltage divided by current. When we divide 1.5 volts by the total circuit current of 0.0407142 amps, we show that the circuit has a total resistance of 36.842182 ohms. You should note the total circuit resistance is smaller than the smallest resistor in the parallel combination. We can also figure the total circuit resistance by using one of the two parallel resistance formulas. When using this formula, we can only calculate for two resistors at a time. When we multiply 100 times 140, our formula becomes 14,000 divided by 240. When we divide this out, we get the equivalent resistance of 58.33333 ohms. We will now use this equivalent resistance and the value of R3 to calculate for the total resistance of this circuit. Our formula now becomes 58.333 times 100 divided by 58.333 plus 100, or 5,833.333 divided by 158.33. It shows that the total circuit resistance is 36.842182 ohms. This is the same resistance value we obtained by using Ohm's law. But we could have also used the formula the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3 divided into 1. Using this formula, our numbers become 1 over 100 plus 1 over 140 plus 1 over 100 divided into 1. This then converts into 1 over 0.02714. When calculated out, it also gives us a value of 36.842182 ohms. Now that we have calculated the circuit resistance and the current flow through each branch of the parallel circuit, we will verify our figures with the digital multimeter. When we measure the total resistance of the circuit, we find that it has a resistive value of 36.8 ohms. In other words, the power source will see a load of 36.8 ohms. When we place the digital multimeter in series with the parallel branches, it shows there is a total current flow of 40.7 milliamps leaving the power source. When the digital multimeter is placed in series with the first branch of the circuit, it shows there is a current flow of 15 milliamps. When the digital multimeter is placed in series with the second parallel branch of the circuit, it shows that we have 10.7 milliamps of current flowing through this branch. And finally, when we place the digital multimeter in series with the third branch, it shows there is 15 milliamps of current flowing through this branch. Kirchhoff's current law stated that the sum of the currents in all the parallel branches must equal the current which flowed into those branches. When we add the currents flowing through R1, R2, and R3 together, we acquire the sum of 40.7142 milliamps, which is the exact amount of current which flowed into the parallel branches. You will find both series and parallel circuits in all types of electronic equipment. You will also find that many circuits are a combination of the series and parallel in a network. These are called series parallel circuits. Here is an example of a series parallel circuit. In this circuit, R2 and R3 form a parallel network, and resistors R1 and R4 are in series with the parallel network. When the current leaves the negative side of the battery, it must first flow through R1, which is a series resistor. From here, the current will divide. Part of the current will flow through R2 and part of the current will flow through R3, since this is a parallel branch. After the current flows through R2 and R3, it will recombine and the entire current will flow through R4. The current then returns to the positive side of the battery. Here we have added values to the resistors in our circuit. Now we can find the total resistance of the circuit. To accomplish this, we must first find the total resistance of the R2-R3 combination. We do this by using the formula R1 times R2 divided by R1 plus R2. We substitute the values of R2 and R3 and our formula becomes 140 times 140 divided by 140 plus 140. Our formula is 19,600 divided by 280. When 280 is divided into 19,600, it shows there is a total resistance of 70 ohms. Therefore, the R2-R3 combination has a total equivalent resistance of 70 ohms. With that equivalent resistance in mind, we must use the formula RT equals R1 plus RE plus R4. RE is a short form to show the equivalent resistance of the R2-R3 combination. Our formula now becomes total resistance equals 100 plus 70 plus 100, the sum of which is 270 ohms. In other words, the power source will see a load of 270 ohms. Since we know the total resistance of the circuit, we can use Ohm's law to calculate for the current flow through the circuit. The formula we must use is I equals E over R. When we substitute the values in the equation, our formula becomes 1.5 volts divided by 270 ohms. When 270 is divided into 1.5, the result is 0.0055555. Since we were calculating for current, our answer will be in amps. Therefore, the current flow will be approximately 5.555 milliamps. We now know the total current flow and the resistance of the circuit, so we will now use Ohm's law formula E equals I times R to calculate for the voltage drop across each resistor. When we multiply the current times the value of R1, we show R1 has a voltage drop of 0.555 volts. When we multiply the current times the R2-R3 equivalent resistance of 70 ohms, we see that R2 and R3 will have approximately 0.39 volts. The actual voltage drop across RE is 0.388885 volts. When we multiply the current times the value of R4, we see that R4 has 0.55 volts across it. When we add the voltage drops together, the sum should equal the power source voltage. The voltage of the battery is 1.5 volts. When the voltage drops are added together, we acquire the sum of 1.5 volts, which is the voltage of the power source. Now that we know the voltage drops across each of the resistors in our circuit, we can calculate for the current flow through each resistor in the circuit. We know that the resistors R1 and R4 are series resistors, so they will have 5.55555 milliamps of current flowing through them. Since R2 and R3 form a parallel circuit, the sum of these two currents must equal the series circuit flow. We also know that the voltage drop across both the components in a parallel branch will be the same. Therefore, we will use Ohm's law formula I equals E over R to calculate for the current flow through the resistors R2 and R3. When we divide the voltage drop across R2 by the resistance of R2, it shows that R2 has 2.7777 milliamps of current flowing through it. When we divide the voltage drop across R3 by the resistance of R3, it shows that R3 has 2.7777 milliamps flowing through it. This is because R2 and R3 are the same value. When we add the current flow through R2 with that of R3, it shows that it is the same amount of current which is flowing through the rest of the circuit. Let's quickly review the material we have just discussed. You have seen that in a parallel circuit, the current will flow into more than one branch of the circuit. The sum of the current flowing through these individual branches must equal the current which entered the branches. You have also seen that the voltage drop for a parallel device will always be the same as the rest of the parallel devices. Here are the two formulas commonly used to calculate resistance values for resistors in parallel. The top formula is used for multiple resistors in parallel, and the bottom formula is used for two resistors in parallel. When you must determine the total resistance of a series parallel circuit, you must obtain the equivalent resistive value of the parallel branches first. Then you simply add the equivalent resistance with the series resistors to determine total circuit resistance. Once the total circuit resistance has been determined, you simply use Ohm's law to calculate the current flow through the circuit. After you have determined the amount of current flowing through the circuit, you use Ohm's law again to determine the voltage drops across the series resistors and the equivalent resistors of the parallel network. As you will recall, the current divides when it reaches a parallel branch. Therefore, to determine the amount of current flowing through each branch of the parallel network, you must use Ohm's law I equal E over R. The voltage value would be the voltage drop which was determined using the equivalent resistance value. The resistance value will be the actual resistor in the parallel branch. Next, we will examine another series parallel circuit. Here we see two parallel circuits consisting of R1, R2, and R3 in one circuit, and R5 and R6 in the other circuit, and they are connected by a series resistor, R4. This circuit is then placed across a 12-volt power source. We will approach this circuit just as we did the last one. First, we must calculate for the equivalent resistance of our parallel circuits. The first parallel circuit consists of a 1 kiloohm or 1000 ohm resistor, a 2.2 kiloohm or 2200 ohm resistor, and a 4.7 kiloohm or 4700 ohm resistor. Remember, the K represents thousands of ohms. We will use the formula 1 over R1 plus 1 over R2 plus 1 over R3 divided into 1. Our formula now becomes 1 over 1000 plus 1 over 2200 plus 1 over 4700 divided into 1. When we take the reciprocal of 1000, it becomes 0.001. The reciprocal of 2200 is 0.0004545, and the reciprocal of 4700 is 0.0002127. When we add these together, our formula becomes 1 over 0.0016672. When we divide 0.0016672 into 1, we acquire the value of 599.80806 ohms. This is the equivalent resistance of the R1, R2, R3 parallel combination. We will round the R1, R2, R3 combination off to 600 ohms. We have redrawn our circuits with the new equivalent resistive values for R1, R2, and R3. We have labeled it RE for equivalent resistance. Its value is 600 ohms. Next, we will calculate for the equivalent resistance of the R5, R6 combination. To do this, we will use the formula RT equals R1 times R2 divided by R1 plus R2. When we multiply R5 times R6, we get 47 million. And when we add R5 and R6, we get 14,700. When we divide 14,700 into 47 million, we get a resistive value of 3,197.2789 ohms. So the equivalent resistance of the R5, R6 combination is 3,197.2789 ohms, or rounded off to 3.2 kiloohms. Now that we know the equivalent resistance of the two parallel circuits, we can use the formula RT equals RE plus R4 plus RE to calculate the total resistance of the circuit. The total resistance of this circuit, as seen by the power source, is approximately 4,800 ohms. Since we know the total resistance of the circuit, we can calculate for the current by using the formula I equals E over R. When we divide the 12 volts by 4,800 ohms, it shows that we have a current flow of 2.5 milliamps. Now we know the total circuit resistance and the total current flow in the circuit. Before we calculate for the current flow through each parallel resistor, we must first determine the voltage drops across each resistor. By knowing the value of the current flowing through the circuit, and by knowing the equivalent resistance in the circuit, we can calculate the voltage drops of the various resistors. To accomplish this, we will use Ohm's law formula E equals I times R. When we multiply 0.0025 times the equivalent resistance of the R1, R2, R3 combination, it shows we have 1.5 volt drop across the parallel network. When we multiply 0.0025 times the value of R4, we see that we have a 2.5 volts across this resistor. And when we measure the current times the equivalent resistance of the R5, R6 combination, we see that it has an 8 volt drop across this parallel branch. When we total the three voltage drops, we see the sum is equal to the power source voltage of the circuit. Next, we will determine the current flow through the various resistors. We will start with resistor R1. When we divide the voltage drop on R1 by the resistance of R1, it shows that R1 has 1.5 milliamps of current flowing through it. When we divide the voltage drop across R2 by the resistance of R2, we see that R2 has 0.6818 milliamps of current flowing through it. When we divide the voltage drop across R3 by the resistance of R3, we find that R3 is passing 0.32 milliamps through it. Since we have 2.5 milliamps flowing into the junction of R1, R2, and R3, we must also have 2.5 milliamps flowing out. When we add the three currents together, we get the sum of 2.5 milliamps, which is the amount that flowed into the junction. R4 is a series resistor, so it will pass the entire 2.5 milliamps. From here the current splits again and flows into the R5-R6 combination. Once again we will use Ohm's law formula I equals E over R. When we divide the voltage drop across R5 by the resistance of R5, it shows that R5 is passing 0.8 milliamps. Likewise, when we divide the voltage drop across R6 by the resistance of R6, we see that R6 is passing 1.7 milliamps through it. When we add the two currents together, we see we again have 2.5 milliamps flowing through this combination. Our final lesson on direct current deals with power. To define power, we must understand that the capacity or ability to do work is called energy, and the rate at which the work is done is called power. Energy's practical unit of measure is the watt-hour. Power's unit of measure is the watt. With direct current, we are always dealing in true power. You are familiar with the term watt with reference to an electric light bulb. A 60-watt bulb consumes 60 watts of electrical energy when it is lighted. A 100-watt bulb consumes 100 watts of energy, and so on. In an electrical circuit, power is equal to the product of the voltage times current. As an example, if our power source is supplying 10 volts and the current is 1 amp, the power consumed is 10 times 1, or 10 watts. E times I, E squared divided by R, and I squared times R can all be used to calculate power in a DC circuit. This calculated power gives the amount of heat dissipated by the resistance of the circuit. For example, a 1 watt resistor is rated to dissipate 1 watt of power. In actuality, to protect the device in a practical circuit, a resistor should have twice the power rating of that required by the circuit. Resistors are only one of the many electronic components measured in watts. You will learn more about power in Part 2 AC. As you have seen, figuring complex-looking circuits can be made simple if they are approached in the proper manner. The first step in figuring the characteristics of any circuit is to calculate for the total resistance of the circuits. In a series circuit, we use the formula RT equals R1 plus R2 plus R3. In a parallel circuit, we use the formula R1 times R2 divided by R1 plus R2 for two resistors in parallel, and 1 over R1 plus 1 over R2 plus 1 over R3 divided into 1 for multiple resistors. The next step is to figure for the total current flow through the circuit. This was accomplished by using Ohm's law formula I equals E over R. Ohm's law was used extensively throughout this program. Once we knew the current flow, we were able to calculate for the voltage drop across each resistor by using Ohm's law equation E equals I times R. When we had finished this process, we knew the total resistance of the circuit, the total current flow through the circuit, the current flow through each device in the circuit, and the voltage drop across each device in the circuit. To gain a better understanding of the material discussed, it is recommended that you draw your own circuits and calculate for the circuit characteristics. You will find that practicing these simple methods will make calculating even complex series parallel circuits almost second nature. If a topic we discussed was difficult to understand, I encourage you to take advantage of the videotape replay and search and reverse to get an instant replay of the material being presented. Remember, a good technician must have a thorough understanding of the basics in electronics to troubleshoot and repair today's complicated electronic equipment.